And what happens if it's going the other way? Now our truck is moving the same direction. That's a truck. And our person throws the ball that way. What does the person on the ground see? Okay. This is sort of a, I don't know, sort of a Japanese version of Mythbusters, I guess. So it'll be very clear here in a minute as to what's happening. You all got it now? The truck's going one way. They've got a pitching machine mounted in the back of the truck, and they're going to shoot a ball out the back at the exact same speed that the truck's moving. Okay, here's the setup. There's the pitching machine. It's just like the guy throwing backwards as the truck goes forward, right? Okay. There's our driver. Safety first. There's our course, right? So they're going to do a couple of laps, and it's on this straightaway right there where they're going to hit their 100 kilometers per hour, and the ball is going to go out at the same speed in the opposite direction, and we will see what happens. Okay? There we go. A couple of test fires, calibrating the speed. They've got it dialed in. Okay, we got the nice black background so we can see the ball coming out. Excellent. That's what it looks like when the car is not moving, right? Okay. What's wrong with this picture? The guy inside is wearing the helmet. There we go. Let's fast forward a little bit here. Here we go. Replay. Now, slow motion. Huh? Look at that. Boy, almost perfect. See that? This stuff works. All right. So very good. Velocity addition. We can add those two velocities, and we get the resultant. This was pretty straightforward, though, because everything's moving in a straight line, right? So you knew the truck, the throw, everything was in the same dimension. It was easy. You just add them up. It's not always that easy, right? So let's see what happens as we get, a little more interesting here. So let's go back to the plane analogy. If the plane is flying well, it would still be fairly straightforward if the plane was going this way. That's the velocity of the plane with respect to the air. And the air was going this way. So I'll use the first subscript as what we're measuring the velocity of, the second subscript as what it's measured with respect to. So this is going to be right, because that's how a plane measures its speed. It measures it with respect to what it's moving through. A boat measures its speed with respect to the water. A car measures its speed with respect to the ground. Vehicles measure their speed with respect to what they're moving through. But if this plane is measuring its speed as a certain value, whatever it is, 300 miles an hour due east, and the velocity of the air is 100 miles per hour due north, then where's the plane going to end up? The plane's going to end up going that way, right? The wind is going to cause it to drift off course. This is the red arrow is going to be the actual path of the plane with respect to the ground. So so what do we do? This is the velocity of the plane with respect to the ground. And how do we find that? It's a vector addition problem. The velocity of the plane with respect to the ground is equal to the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground. That's our formula. That tells us how we do this. In this case, it's fairly straightforward because I gave you a right triangle, right? You can figure this out pretty easily without even going to your trig functions. But if it wasn't a crosswind, if the wind was at some odd angle, then it would be a little more difficult, right? Then you need to get into your trig functions. So this equation guides us. Let me sort of draw it out generically. The velocity of A with respect to B, A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C. And the first subscripts have to be the same. The last one has to be the same. And these two in the middle have to be the same. And if you can get it into this format, then that tells you what vectors you need to add, because sometimes it's a little confusing. If you have two cars moving toward each other and you're trying to measure the velocity of one car with respect to the other car, it's not as straightforward as these problems. Well, we could get to that. Yeah. To this one you can, the plane and the crosswind, yeah. Because I said the crosswind was 90 degrees to the motion of the plane. Yeah, the plane's going east and the wind is going north, so that's a 90-degree angle. But this equation is always true. They don't have to be 90 degrees to each other. This is always true. So if our wind was at some angle, we would still do the same thing. We would have the plane with respect to the air. Maybe the wind is blowing this way. That's the air with respect to the ground. And what's our plane doing? Our plane is doing that. Okay? The first vector, A with respect to B, that's the plane with respect to the air. The second vector, the air with respect to the ground. And our resultant is the plane with respect to the ground. So it's a vector addition problem. And in this case, you'd want to break up that second vector, right, the air with respect to the ground. You want to break that up into an east and a north component, right, an x and a y component. And then you can add components together and figure out what your resultant is. We'll do that more in lab.